will cover everything else that is necessary in this course itself. So initially, when we do the preliminaries, we'll do it a little quickly. You'll be expected to fill in a lot of details, but we'll start from scratch. So in any case, if you have any questions, please feel free to stop me in between. I may not always monitor the chat box, so you can just unmute yourself and ask. All right. So when we're dealing with information theory, we're always talking about sort of large system limits. Typically, we will study problems where we deal with a large number of channel users, a large amount of time, or a large number of users. And in order to make technical arguments, to make mathematical arguments, we have to be careful when we define notions of limits and sequences and so on. Right? So we will formally define what a sequence is, what a limit is, when a limit exists, when it doesn't exist. Because after all, when we analyze systems, we have to be careful when regarding the statements that we're making. So these are all, of course, basic concepts which you have seen in previous classes, but perhaps not with that amount of carefulness you might have studied. Okay, so generally these topics are covered in any graduate level course on real analysis, and if you are interested in exploring more, then you can pick up any book on real analysis and go through that. And one good book is this book called Analysis 1 by Terence Tao. It's a good place to start. Terence Tao has two books, Analysis 1 and 2, and 2 covers more advanced topics. But of course, this is more of a crash course more than anything else. We will not go into too much detail. Okay, so let's be careful and define what a sequence is. Right? Can anyone give me a definition of a sequence?
It's like a collection of objects which arranged in some manner, like some pattern.
Okay, so it's a collection of objects. So it's an ordered collection of objects. Okay, that's a good intuitive way to start. Any other definitions? Anyone else? So in particular, is the set of objects finite or infinite?
Infinite.
Yeah, so it's typically infinite. So we'll use a slightly more formal definition of a sequence. We'll say that a sequence. So to define a sequence, the objects must come from some set. Right? So we'd say that a sequence over some set A, let's call it A, is basically, mathematically speaking, this is just a map. It is a map from the set of natural numbers. So the set of natural numbers is 1, 2, 3 up to infinity to this particular set. Right? So this is one way of looking at a sequence, but more intuitively, it is just an ordered collection of objects from the set A, right? So for example, when I define a sequence 1/2, 1/3, 1/4, and so on. So what is the map? What is f of n equal to?
One by n.
It is just 1 over n, right? Similarly, when I have, say, 1/2, 1/4, and so on, my f of n is 2 to the minus n. All right. So basically, it is, so when we say that we have a sequence, it is, you're basically defining a function which maps 1 to f of 1, 2 to f of 2, 3 to f of 3, and so on. And that's all that a sequence is. Right? And but what we're really interested in when we're talking about sequences is what happens in the limit, right? And our goal is to understand what the limit of any given sequence is. Right? So the first question is, does every sequence have a limit?
So no, not necessarily.
Not necessarily. Right? So can you give me a sequence which has a limit?
Like, sir, any convergent sequence.
Correct. But can you give me an example of a convergent sequence?
So written over the f of n equal to 1 by n. It will
Sure. Okay, so f of n equal to 1 over n. This has a limit. So we say that the limit, that the sequence converges, or it's a convergent sequence. And the limit in this case, what is the limit? It's equal to 0. So the limit as n tends to infinity, 1 over n is 0. Right? All right. Yeah, so thanks, Ashish. I made a mistake in this. So f of n in this case is 2 to the minus n plus 1. Yeah, so can you give me an example of a sequence which does not have a limit?
So f of n equal to n or n square.
Okay, so that's a good example. So look at two classes of examples. One where, say, f of n is equal to n, or f of n equal to n square. So these are divergent sequences, whereas these, as we know, are convergent. Right. Okay. So this is a case where, as n tends to infinity, f of n also tends to infinity. We could also say n or f of n equal to minus n square, in which case it goes to minus infinity. All right. So any other kind of example? Yeah. So Chandramouli has one example, and that is f of n equal to minus 1 raised to the n. Right? So this is an example of a sequence which is not bounded, and therefore it diverges. Whereas this is an example of a sequence which is bounded, but even then it is divergent. Okay, and a good part of this class will be about studying when a particular sequence converges, when it diverges, and what can we do if the sequence diverges. All right. So now, note that we give a formal definition. So we can define a sequence over any set, right? In particular, so these are real valued sequences over here. But then you could define sequences over rationals, you could define sequences over the integers, and even you could have sequences over, in particular, you can define it over any metric space. Okay, so one example of a sequence is the following. F of n is, so now f of n is not a real number. We can say that f of n is a vector, right? So in particular, I could say that this is 1 over n and say n. All right. So does this sequence have a limit? Does it converge? No, it does not converge, right? And we'll see the definition of a limit so that we can handle even such examples. So here is an example which does converge, or say 1 over n 2 to the minus n. Right? So this is an example, I claim that this is an example of convergent sequence, and we'll see what makes this convergent, how do we define the limit of such a sequence. Right? So I mean, you can already tell me what the limit of this particular sequence is. What is the limit of this sequence? So it's the zero vector. So it is 0, 0. All right. Okay. So these are examples where the sequence it's clear that the sequence does not have a limit. In particular, the example over here. So here is a sequence. So this is an example of a sequence which is not bounded, so it diverges to infinity. And this is an example of a sequence which is sort of oscillating, right? But then, since we're defining it over some particular set, it may be possible that the sequence converges, but does not converge within the set that it is defined on, right? So in particular, we will say that the sequence does not converge. So for example, let's look at sequences defined over the rational numbers. Okay. So does every rational sequence have a rational limit? Is it possible to have a rational sequence, but it converges to something else? Yes? So can a rational sequence have an irrational limit? Okay, so almost says every rational sequence has a rational limit. Anyone else? Any guesses? Okay, so Sohit Kumar has an example. So E, can you tell me what the sequence is which gives you E?
Like I thought the sum 1 plus x plus.
Okay, good. Go on. So I need something in terms of a sequence, right? I need some kind of a sequence. So can you tell me what that what would f of n be? In order to define a sequence, I need to define f for every n. Right? You're right. So E is one such example. Can you?
Sir, expansion of that exponential function e raised to power x, or if we are supposing x equal to 1, then 1 plus
Okay.
1 by factorial n factorial 2n.
So it's 1 plus 1 by yeah. So is it x power n by n factorial, Shantanu, or something else? So in particular, what is this summation I going from 1 to n of 1 by n factorial?
Yes, sir.
Sorry, I factorial.
I factorial.
It's not I factorial. I factorial. So note that for every finite n, this is, it's a series, yes, but then for every finite n, this gives me a number, right? It gives me some number which is going to be a rational, right? You're right that it is indeed a series, but a series is essentially for every finite. So if you look at the individual, the finite sums corresponding to the series, each of that is also a sequence, right? That corresponds to a sequence. So if I define f of n to be summation I going from 1 through n of 1 over I factorial, for every finite n, this is certainly a rational number, right? But then as n tends to infinity, this does not tend to a rational number anymore. It's an irrational number. So this is an example of a rational sequence having an irrational limit. And in fact, you can, there are different ways to define such sequences, or different examples that you can come up with. In particular, you take any rational number, any irrational number, let's say pi. Okay, and I'll define f of n to be the first n decimal places of pi, right? So for every finite n, so let's say f of 1 is say 3.1, f of 2 is 3.14, f of 3 is 3.141, and so on, right? So here for every finite n, it's a rational number, but then it does not converge to a rational number. It converges to an irrational number. Okay, and this is an example of a sequence, a rational sequence, but it does not converge to a rational number. Okay? So you have to be careful in defining. These are just minor technicalities, but wherever we're talking about, say, sequences over the real numbers, or sequences over real vectors, or sequences over complex numbers, the sequence will always converge to a real number or a complex number. Right? So any questions so far? Right. So we need some more tools to understand what convergent sequences are, divergent sequences are, and what do we do if a sequence diverges. Okay. So given any set, so we've seen that over some sets, sequences can converge. Over some sets, sequences may not converge to something within the set. All right. So in particular, if I define the set A to be, let us say, 0, 1. Okay, so it's the open set 0, 1, and I look at the sequence f of n equal to 1 over n. Okay, or maybe 1 over n plus 1. Okay, so each element of this sequence, so this is just half, 1/3, 1/4, and so on, right? So what does this converge to? Converges to 0, right? So f of n converges to 0, but 0 is not in this particular set. Okay. So there are certain sets over which the sequence converges to something within the set. There are sets for which the sequence may converge to something outside the set. Okay. So given any set, all right. So given any set A, in particular, we'll always look at subsets over the reals. So the supremum of a set A is basically defined as follows. Okay, so we say that little a is the supremum of the set A if the following two conditions hold. So firstly, we want A to be greater than or equal to all x in A. Okay, so it's going to be what we call an upper bound for A. So it has to be an upper bound for A. And a supremum is basically what I call a least upper bound for A. So it's the smallest number A such that it is greater than every number in the set A. So in particular, if you take any small epsilon, so you take A and then you try to shift a little below A, then you'll always find a number which is greater than this. So so basically you pick any epsilon greater than 0, then you can always find some x in the set such that A is strictly less than x minus epsilon. Right? So this is a least upper bound for A. Okay, so let's see an example. Okay, so let's say that A is the set that I have above. It is 0, 1. Right? So what is the supremum of the set A? Yes, anyone? Right. So it's just 1, right?
So supremum should be lie inside the set, or it should be not necessary to lie inside
That's
the
a
set?
very good question. So in this case, so I claim that the supremum of A is equal to 1. Okay. So now does 1 lie in the set A?
No, sir.
It doesn't, right? So in general, the supremum of A is a real number which may or may not lie in A. So the supremum, so it's a very good point. The supremum may not lie in the set. So it may not lie in A. Okay. But can you give me an example of a set where the supremum lies within the set?
Sir,
Yes.
sir, can you please explain the second point in the definition once?
Okay. So the first point is that, of course, A should be greater than or equal to x for all x in A. So in this particular example, A equal to the open set 0, 1, you have 1 being greater than or equal to x for all x in A. Right? That's obvious. The second point says that if you pick any epsilon, so if you try to go a little below 1, so you take 1 minus epsilon. So pick some epsilon, say epsilon equal to 0.0001. Okay. Then you will always find a point in A which is strictly greater than, this should have been such that x is greater than A minus epsilon, or A is less than x plus epsilon.
Okay, sir. Understood.
Yeah, thanks for pointing that out. So if you take 1 minus 0.0001, which is basically 0.9999, you can always find a point which is greater than x, greater than this, greater than A minus epsilon, but lies in A. For example, 0.99991 lies in the set A. Okay? So similarly, you can define the infimum of a set, the infimum of A, which basically satisfies two properties. Can someone tell me what it is? What is the first property equivalent to this?
Should be less than equal to x.
Correct. So A should be less than or equal to x for all x in A. So in other words, A should be a lower bound for A, and should also be the largest lower, the greatest lower bound. Okay. So, and then what is the second point?
So sir, inequality will be changed that.
Correct. So there should exist some x in the set A such that x is less than A plus epsilon. Okay, so basically if you draw the real line, right, so you have some set, okay, maybe the set is what I've shaded over here. It need not be a connected set, so it is some set A, right? So it's a greatest lower bound, so it's the supremum if, so we say that this is the supremum if of course everything lies to the left of, if the whole set A lies to the left of this point in the real line, but also if you go a little to the left of this point, then you will find something in between. So if you go a little to the left, then there is some point in A which lies in between these two. Right? So this is A, this is A minus epsilon. Similarly, for the infimum, we say that, say B is the infimum. If you look at any B plus epsilon, then you can always find some point in between. Yes. So if the supremum lies within the set A, then we say that let me just scroll down. So if supremum over A lies in the set A, then we call it the maximum of A. And similarly, if the infimum lies in A, then we say that we call this the minimum of A. So for any set A, any subset of the reals, so every subset of the reals has a supremum and an infimum. So these two are well defined for every set, but the maximum and the minimum need not be well defined. So in particular, if you look at the set A over here, this has a supremum and an infimum, but it does not have a maximum or a minimum. There's one more special thing, that it's again a technicality. But so for example, if you look at the set, so let us define the set to be the set of all, say, 1 over n, such that n is in the set of integers. Okay. Sorry, not this. So, to say to the n, where n is in the set of integers. So what is the supremum?
Is it infinity?
Yes, so supremum is infinity because
Like
as n tends to minus infinity, 2 to the n, sorry, as n tends to infinity, 2 to the n also tends to infinity. So we say that the supremum of A is infinite, although infinity is not a real number. We say that if it is unbounded, then we say that the supremum is infinity. Similarly, if it is not bounded from below, if it tends to minus infinity, then we say that the infimum is minus infinity. So in this case, what is the infimum of the set?
One.
Yes. Are you sure?
So yeah, it
should be 0.
Exactly. So it's 0, right? So because I'm allowing n to be negative, so n can be -1, -2. As n tends to minus infinity, this tends to 0. Okay. So what if a was -2 raised to the n? So what is the supremum of a?
Sir will not define.
Why not? Why is it not defined?
Sir, it will depend on n, whether it is positive means odd or even kind of thing.
It's okay, right? So it's a set, right? So remember, we're not talking about sequences. So this is just a set. So it is a set of all numbers which can be written as -2 raised to the n.
Okay, yes, sir.
Correct? And we just want to know what the supremum and the infimum are. So Anu is right. So the supremum of this set is again infinity. What is the infimum of this set? Okay, Chandramoli says that it is the same as before. Are you sure? Is it 0?
minus infinity, right?
Correct. It is minus infinity because as n tends to infinity, you have both +2 to the n and -2 to the n. So it's if n is odd, then this becomes negative and goes smaller and smaller. So the infimum of a is in fact minus infinity. And if you view this as a sequence, so if you look at f of n equal to -2 whole raised to the n, then this is a divergent sequence. So for even n, it's a growing sequence, it's monotonically increasing sequence, and for odd n, the corresponding subsequence is monotonically decreasing. All right, so all of these points, the supremum and the infimum, are typically what correspond to what we call limit points of sets. So
Sir,
yes, yes, please.
sir, like in general, like the supremum or supremum or infimum is calculated like if we calculate the limit as n tends to infinity and n tends to minus infinity, or is there any method to find that supremum or infimum?
Or to find the supremum and infimum. So some sets it may be easy to find the supremum and infimum. Sometimes it may just be very complicated, depending on the set that you have.
So in general, like if we put n tends to infinity something, then
It depends, right? So it's not necessarily a sequence. So we're defining suprema and infima of arbitrary sets.
yeah,
It could be a continuous set. It could be a discrete set. We don't know.
okay.
So if it's a discrete set, sometimes it's easier. In many cases, we can just look at the set and say what the supremum and infimum are. But in some cases, it may be very difficult.
Okay, sir. Okay.
Right? So that is what distinguishes these two. And in particular, if the set A is closed, right? If it's not an open set, is closed, then the supremum is equal to the maximum. So the maximum exists, and the minimum also exists. Right? But if the set A is open, then the supremum, if it may or may not. If it is, yeah. So if it's open, in general, the supremum may not be equal to the maximum. That is, the maximum may not exist. Okay. So our ultimate point, of course, is to understand what the limit of a sequence is, and in order to do so, and we know that the limit of a sequence may not always exist. There are sequences which diverge, and therefore the limit is not well defined. But then, just like we have the infimum and supremum, which you can define even when there is no maximum or minimum, we will define two other notions: the lim sup and the lim inf, or the limit superior and the limit inferior, which exist for any bounded sequence. Okay. So before we even go to that, okay. So Sivamoni has asked a question. So there are a couple of questions in the chat box. So one question is, supremum and infimum defined for all types of sets. So for any subset of the real numbers, the supremum and infimum always exist. They may not lie within the set, but they could lie. But supremum is always some real number, or it's infinity, and the infimum is always a real number. It always exists, or it could be minus infinity. So for complex sets, we don't have any order, right? So we're defining the supremum and infimum only for real sets. Okay. So if the maximum exists, then it is always equal to the supremum. If the minimum exists, then it is always equal to the minimum. It is always equal to the infimum. Any other questions? So these notions are very closely related. They're very similar, but sometimes you need to be careful. Right? So the supremum will always exist, the infimum will always exist, but the maximum and minimum may or may not exist. Okay. So before we see what we can do about divergent sequences, let us see what we can do. How do we define a convergent sequence? Okay, so in order to define a convergent sequence or to define a limit, we need some notion of a distance. Okay, so suppose that we have a set A, and on the set we have some notion of distance. So in particular, very commonly we use the set R, and the distance is just the absolute value of the difference between two numbers. Right? But in general, you could define, let's say, RD, sorry, let me not use D, let's say RK, and D is the Euclidean distance between 2 points, or it could be the L1 distance, or in general, some kind of a distance. Okay. But most commonly, when you talk about sequences, you look at real valued sequences with the absolute value of the difference between 2 points. Okay, so given such a set with a distance associated with it, and if you have any sequence f of n, so any sequence defined on this, so if fn, so I'll use the following notation to define a sequence. So if fn is a sequence over A, then we say that fn converges to some A, or the limit as n tends to infinity, fn is equal to A if the following holds. So you take the point A and you take any neighborhood of that point. Right? So for all sufficiently large n, the sequence should lie within that particular neighborhood. Okay, so in particular, let's take the following example. Okay, so let me complete the definition first. So if you take any neighborhood, or if you take any epsilon greater than 0, you will always find some m such that d fn comma a is less than or equal to epsilon for all n greater than or equal to m. Okay, so basically for sufficiently large n, all the points of the sequence are going to be epsilon close to the limit. Okay, so again, let's take an example. So let us take f of n equal to, say, 2 to the minus n. Okay, so we know that the limit exists, and that the limit as n tends to infinity of 2 to the minus n is equal to 0. Okay, so formally speaking, you should, if you pick any epsilon, any small epsilon, you should be able to find an m such that 2 to the minus n minus 0, the absolute value of the difference, is less than or equal to epsilon for all n greater than or equal to n. So can you tell me what the m would be in this particular case? Correct. So it's log 1 over epsilon. So basically, we want to make sure that 2 to the minus n is less than or equal to epsilon for all n greater than or equal to m. Or in other words, if I take log on both sides, minus n should be less than or equal to log epsilon, or n should be greater than or equal to log 1 over epsilon. Right? So in this case, the corresponding m is log 1 over epsilon. Okay. So let's do one more example. So let's take f of n equal to, say, log 1 plus 3 over n. Say base 2. Okay. So now, if I fix an epsilon, so firstly, does this sequence converge? And if so, what is the limit?
0.
Correct. So it converges to 0. Okay, and what is the corresponding n? So if I fix an epsilon greater than 0, then I want to show that there is some m such that log 1 plus 3 over n is less than minus 0 is less than epsilon. Less than or equal to epsilon. Alright? And
N maybe 3, sir.
n is 3. And why do you say that?
At n equal to 3, this f of n will be 0.
At n equal to 3, are you sure?
Become 1 then.
It will be 1. It will be 1.
It will be 1, right?
Gotcha. It will be 1.
So can you come up with an m? So basically what we want? We want to make sure that we want to find beyond, so basically beyond some particular point in time or point in n, this is going to be less than, it's going to be epsilon close to 0, right?
So 3 by 2 raised to power epsilon minus 1.
So log 1 plus 3 over n should be less than or equal to epsilon, or 1 plus 3 over n should be less than or equal to 2 to the epsilon, right? Or 3 over n should be less than or equal to 1 plus 2 raised to epsilon. So n should be greater than or equal to, as Ritesh mentioned, 3 over 1 plus 2 raised to epsilon. So the corresponding m is basically 3 over 1 plus, or CL of 3
So
over
minus
1.
1. 2 raised to power epsilon minus 1. That's what
Sorry. That's correct. Yes, that's right. Okay, so this is an example. So now that we understood what limits are, we know that not all sequences have limits, right? So let us look at f of n equal to minus 1 raised to the n. So you pick any point, right? There is one subsequence which converges, so it's always either plus 1 or minus 1. Right? So you pick any point, let us say plus 1. For all sufficiently large n, or in other words, you can find an epsilon such that for all sufficiently large n, you will always find points outside 1 plus epsilon or 1 minus epsilon. Right? In particular, let us say that you take epsilon equal to 0.1, then you can always find points such that f of n minus 1 is greater than 0.1. And similarly, you can also find points such that f of n plus 1 is greater than 0.1. Right? Because for every odd number, f of n minus 1 will be greater than 0.1, and for every even number, f of n plus 1, the absolute value will be greater than 0.1. So yes, so to answer Chandramoukhi's topic, we will be getting into the communications aspects, but now we're basically defining the language that is necessary. Right? So I'll leave you off with one maybe final definition. So we know that the limit may not always exist, but then I define the following: the lim sup of a sequence is basically the following. So it is a limit as n tends to infinity, the supremum over all n greater than or equal to m of f of n. Okay, so and similarly we'll define something called the limit f of n infinity, which is the infimum over all n, m greater than or equal to n of f of n. Okay, and we'll see that these two are always well defined, and therefore for any sequence, even if it is convergent or divergent, these two quantities can always be defined. So here's an exercise for you. So prove that every sequence which is bounded from above always has a limit. Okay, and every sequence which is bounded from below, every real sequence bounded from above has a limit, and every decreasing real valued sequence which is bounded from below always has a limit. Okay. So we'll stop here for the day, and we'll continue in the next class. But if you have any questions, please let me know. Yes, ma'am.
Sir, what do you mean by like a sequence bounded from above and bounded from below?
Okay, so basically it's a sequence bounded from above if it does not tend to plus infinity. Right? It's bounded from below if so we say that some sequence f of n is bounded from below if you can find some alpha such that alpha, so f of n is always less than or equal to alpha, and it is bounded from below if you can find some number such that f of n is always greater than or equal to beta.
Okay, sir. Okay.
Okay. So you can find a real number beta, right? Not plus infinity minus infinity. So for example, minus 1 raised to the n is a bounded sequence. It is bounded from above by plus 1 and bounded from below by minus 1. It's also bounded from above by plus 2 and bounded from below by minus 2. But this is a bounded sequence, but it does not converge. All right, but the claim is that if the sequence is increasing and it's bounded from above, then it has a limit.
Got it, sir.
Okay. Any other questions? Right. So the scribed lecture notes will be just evaluated. So it's not like a traditional exam. So you will submit scribe lectures. I may ask you to make some changes. If there are some corrections required, you can discuss and then submit. So it's so the part for the scribe lecture notes comes as long as you just give a decent enough set of lecture notes. Any other questions? So I'll put up the sort of mapping from classes to students. So hopefully by tomorrow we'll know the set of all students who have registered for the course, and then I'll mention who gets to scribe which lecture. So you can take maybe a week or so to scribe the lecture notes for that particular class and then submit it. If there are any changes required, some more details that you need to fill, or there are some corrections, I will let you know, and then you have to just make those changes and then send it.
Sure.
Yes, Soiko.
In AIMS, it was not changed, I guess, to slot C.
Yeah, correct. So as I mentioned, you can maybe wait till around 3 p.m. today. If the change is still not done, then just send me an email. And anyway, just send me an email, even if you're not able to register because it's not changed on AIMS. I will send an email to the ACAD section to let you register anyhow, even if they don't make that change in the time slot.
Okay.
Any other questions? Okay, so if there are no further questions, then for the day, we'll meet again on Wednesday.
Thank you, sir.
Thank you.